Okay, so I suggest we start. I hope you can still all hear me. It's really my great pleasure to introduce Lexing Ying for this trilogy of lectures that he kindly agreed to give today for the first one. So let me just say a few words about Lexing before I hand over to him to start his lecture series. So Lexing Ying is a professor of mathematics at Stanford University. Lexing has made really various substantial contributions at this interface between mathematics, in particular computational mathematics, and machine learning, in particular deep learning, that he will share with us today. His work has been acknowledged by various honors and prizes. I'm not going to mention all of them, but just a few kind of cornerstones. He got in 2013, he got the James Wilkinson Prize in Numerical Analysis and Scientific Computing from SciAm. And very recently, actually, for next year, he has been invited to give an invited lecture at the ICM, at the International Congress of Mathematicians, which is a great honor, in particular if you're working in this field of mathematics at the interface to applications. So I think that's really wonderful. So it's great. You're going to pioneer the Mathematics Congress for us. So today, Lexing is going to start, as I said, his trilogy of lectures on selected topics on mathematics of deep learning. He's starting today with neural networks and PDEs, and then we'll continue tomorrow and on Thursday at the same time with other topics. And I should also remind everyone that this talk is being recorded. So if you don't want to appear on the internet, then maybe turn off your camera. And yeah, so otherwise, if you want to ask questions, I don't know, Lexing, how you want to handle it, whether people can just interrupt or whether we should just collect, you should wait till the end. Maybe you can just say that before you start. And yeah, I'm going to hand over the word to you. Thank you so much, Lexing.
Yeah. Thank you, Carola. Yeah, so first I'd like to thank Carola and also the Newton Institute for the invitation to allow me to give this talk. And in terms of the questions, I think the audience is not very large right now. So, I mean, anyone can just interrupt me if you have a question, okay? So I like to make this as interactive as possible. So these are going to be 3 lectures. And today I'm going to talk about neural networks and also partial differential equations. So this is sort of like an overview talk where most of the work, I want to first claim that I'm by no means an expert in deep learning and by no means an expert in partial differential equations. But what I just want to share with you about how I think that the neural network can help PDE and also how PDE can help neural network. So this is kind of like the overview. So it's kind of like one of these talks with 1 slide per topic. So but I just want to give an overview about where the field stands as how I view it. Okay, and the second talk was going to be inverse problem, and the third talk is going to be some theoretical understanding about generalization. Okay, so let me get started. So the topic is neural network and also partial differential equations. So we have all know that in the past few years, or maybe by now it's probably almost 10 years now, the neural network has made a big impact on many things, starting from machine learning, AI, now these days to sciences. So the way I view it is that, I mean, I think it's a general consensus that the most important thing about neural network for us, for people doing computational math and applied math, is that it's a really flexible way of representing high-dimensional objects, like high-dimensional functions, high-dimensional maps, and high-dimensional distributions. Okay, so here I just put a few pictures I took from the internet. These are pictures about what are the common neural network you see these days, starting from fully connected neural network, convolution neural network, residual neural network, and ResNet. Okay. Now, as I said at the outline of this talk, the talk has two parts. The first part is about how the neural network can help solve PDEs, and I will give you a few examples about this. And then the second part of the talk is how the PD is going to help explain certain phenomena in neural networks and also help us develop a new tools and new structures in neural networks. All right. So part one, okay, neural network for PDEs. So here I'm going to split this part into three small sections. We're going to start talking about high-dimensional PDEs. I think this is one place where neural network play a huge role. And then I'm going to move down to low-dimensional PDEs. These are the PDEs that we use quite often in daily life. And finally, I'm going to briefly talk about the high-dimensional to low-dimensional reduction. So if you have a high-dimensional PDE and you want to reduce its dimension, how the neural network is going to help us. Okay, it's a dimension reduction, model reduction problem. Let's start from the first part of the first part. Okay, so so for high-dimensional PDEs, typically, and the neural network comes in as a way to represent the solution of the PDE. So here I'm going to consider three examples. These are all three high-dimensional PDEs. The first one is a many-body shorting equation. It's in quantum mechanics. The second one is molecular dynamics. And the last one is control problem. So we all know that shorting equation could be very high-dimensional if you study many, many particles. So here we're mostly going to study fermions, for example, like electrons. Okay? So in quantum mechanics, so we're given a Hamiltonian, which I denoted by H here, and we assume that our system have about n electrons, so it's an n-body Hamiltonian. And one of the fundamental tasks of many-body shorting equation is to find the ground state and the ground state energy. So essentially, what we want to do is that we want to minimize over all the possible wave functions. Here we require it to be anti-symmetrical wave functions because they're working with fermions. This Rayleigh quotient, which is phi h phi over phi phi. Okay. Now, this phi is a high-dimensional wave function. So traditional methods like finite element, finite difference doesn't work very well if you have many electrons. So chemists came up with various kind of special ensembles, starting from Hartree-Fock density function theory, go all the way to Monte Carlo techniques. Now, the way neural network comes in is that neural network provides a way to parameterize this high-dimensional wave function with a set of parameters, which we denote by theta here. Okay, so once you parameterize this neural network, this wave function with neural network, then you obtain a reduced Rayleigh quotient problem. So we're optimizing over the parameter theta now. This phi theta h phi theta over phi theta phi theta. Okay. Now this is not 100% new here because the chemist has been doing various kind of parameterization for 50, 60 years. But I think the new thing is the neural network is extremely flexible, and also automatic differentiation, differential programming allows to do optimization of this quantity much more easily. Now, let me give you one example. It's called variational Monte Carlo. So in the variational Monte Carlo, what we do is that we're starting from this minimization problem, but we transfer this into integration type of problems. So the way we do that is to just do a very simple rewriting of the top part of this ratio. So here is phi h phi, but what we do is that we multiply with phi and divide with phi. Okay, so once we do that, this Rayleigh quotient turns into this form. Now, the beautiful thing about the right-hand side is that now you have this phi square pops up. So therefore, what we can do is that we can treat phi square as a probability density and use Monte Carlo techniques to calculate the bottom part and also calculate the top part. Okay. Now, this is a big field, so I'm only touching the basic surface here and try to give some basic ideas. Now, one question is that what are the neural network architecture that has been used in the literature? So in the past few years, there's a lot of work has been proposed. So one example, for example, is this called FermiNet has been proposed, which has obtained quite a lot of success. And So in the Fermi-net and also in many other papers, one way is to use something like the following: is that decompose a wave function into two parts. One part is a symmetric exponential of a symmetric function, and the second part is an antisymmetric function, both parameterized by the parameter theta. So the antisymmetric function nicely taking care of these, the slated determinant nicely taking care of the antisymmetric part. And the first part, all you need is the symmetric function and greater than 0. So therefore, we put an exponential here. Now, there are more advanced techniques such as backflow, which is really a theta parameterized differential diffeomorphism for the parameter x. All these techniques has also been used. But you see that so these things, even though I give you a high level description of this, but when you actually implemented it, it can be quite technical. So without the automatic differentiation tools provided by neural network, it was very difficult to do. But now these days with neural network, this become possible. So one interesting theoretical question that remains is the following: is that once you solve for theta star, theta star, and you can plug in to get your neural network wave function, that phi star. Now, what's the difference between the neural network wave function and the true ground state wave function? So this is as for mathematicians, this is one question that we need to understand. So far, there has been work for two-layer neural network for simple eigenvalue problem. So this is work that come from Jennifer Lu's group at the Duke. But for more general problem like what we have here for electrons, this is still yet to be, and for more complicated neural network structures, like the one that I described here, it still needs to be worked out. Okay. So the second example I'm going to give is high-dimension problem, is molecular dynamics. So here I'm going to use this simplest equation for molecular dynamics. This, in some sense, is oversimplified. This is called the overdamped Langevin dynamics. So in the case of overdamped dynamics, my molecular dynamic, my molecule has been described by a particle by the coordinate x belongs to R3n. So you can think about that. I have n atoms, and so each of the atoms has three-dimensional coordinate. So you put them all together, you get a vector in R3n. Now here we make the simplifying assumption that this molecule system is just moved under the gradient descent motion with a noise. Okay, so in most of the cases you will work with underdamped Langevin equation, but here I'm just, in order to simplify the presentation, I'll work with overdamped Langevin. In the case of molecular dynamics, you care about quantities such as reaction rate, transition rates, and also transition passes. So, one of the simple example which is related to this quantity is something called a commuter function. So the idea of the commuter function is the following: is that it's defined the following: for every spatial location x belongs to R3n, ux is defined to be the probability of starting the process from location x. It arrives at set A first before it arrives B. So A and B are two sets which are called metastable sets. These are supposed to be the locations where you have a very low energy and your molecule prefer to stay in these configurations. So what I'm saying here, start from any point x, your process is going to wander around, sometimes going to hit A first and then go to B. This quantity is asking, what's the probability that you hit A before you hit B? Now, this quantity U is a high-dimensional function because it's defined on R3n dimensional space. And luckily, it satisfies the following equation, which is a static Fokker-Planck type of equation. So these two boundary conditions essentially says that if you start from A, you're going to reach A first. And if you start from B, you're going to reach B first. So it's consistent with the picture that I described here. Now, how do we solve this high-dimensional static Fokker-Planck type of equations? So luckily in this case, and in a few other cases as well, is that we have a variational formulation for our PDE. So in fact, the U star, the commuter function, in fact, to satisfy the following is actually the argument of the following quadratic variational form. And here, this is just a gradient. It's the same as when you see in the Laplace equation, but the difference is that you have this probability weight here, which is derived from your inverse temperature and also your potential function. Now, how does a neural network come in? Well, the neural network come in again as an ansatz to represent this high-dimensional function. And in fact, you can be quite flexible about what kind of neural network you want to use. And once you decide a neural network architecture, and then you can plug in. So in the previous formula, what you do is that you replace this with u theta, and now it becomes an optimization problem in theta, and you can start optimizing using stochastic gradient, atom, and then that will produce a result. And again, the question here is that how good is a neural network solution compared with a true solution? And this is also an active direction, and I think it's so far we will have very preliminary result for two-layer neural networks for simple elliptic problems. But in general, this is a hard question. So the third example I'll give you in high-dimensional PD is this Hamilton-Jacobian-Bellman equation. So here I wrote down two equations, but they're really very similar. So one is for the finite time horizon case, and the second one is for the infinite discounted time horizon case. No, infinite time case. Now here, the x variable typically is denoted by a state. Is this, for example, in mathematical finance applications, x corresponding to, for example, the current configuration of your portfolio. So what you want to do is that you want to decide what action to take so that you can maximize, for example, your profit. Okay. So this formulation essentially is a dynamic programming formulation, and this has been the cornerstone of designing algorithm for Hamilton-Jacobi equation. Now, in the field of machine learning AI, and this problem is typically called the Markov decision process or reinforced learning. Okay, so when you know a lot about your model, about here, what I mean is really this operator L and this reward R, then this is typically called Markov decision process. On the other hand, if you don't know much about your model and you have to discover your model along the process of interacting with the environment, and then this is called reinforced learning. Now, as a dynamic programming problem, and this control problem typically can be formulated in linear programming. So in fact, if you take a look at the literature, and my group also done some work on that, is that you can write down dual formulation, primal formulation, and also the primal dual formulation for this Hamilton-Jacobi-Bellman equation for the control problem. And in fact, the primal formulation is associated with this so-called value iteration and policy iteration. Dual formulation is associated with a policy gradient type of methods, and primal dual problem is writing this in terms of minimax problem, which without much constraints. So all these can be developed into efficient algorithms. Now, again, neural network comes in as a way to parameterize this value function V. Recall, because X could be high dimensional, so V is a high dimensional function, so traditional numerical methods doesn't work, and neural network came to help here. Now, when we parameterize these V with a neural network, in the literature, this is typically called a value function. There's also another formulation. Instead of studying the value function, one studies of some quantity called a Q function, where Q function is a function of the state X and also the action. This is expected reward from a state X if the user take action A immediately. Okay, so expectation is not on the current action, but on all the future actions. The current action is going to be A. So this has a certain advantages, and in the literature, this is called a deep Q network. Now, deep Q network played a big role in, for example, in the AlphaGo's success in playing the Go game, and is also it has been used tremendously in the reinforcement learning community. Now, these are all empirically, the value network and deep Q network have been very successful for solving reinforced learning problems. Now, however, I think it's fair to say that at this point, there's no mathematical rigorous convergence guarantees for most of the neural network algorithms applied to reinforced learning and MDP. Part of the difficulty is because when you start a nonlinear approximation like neural network, and for example, in the primal dual formulation, which by minimax theorems, guaranteed to have a unique solution, but when you start nonlinear approximations, and these guarantees are off. You have to, this is a challenging direction. Okay, now we move to the second part of the section 1. So here I'm going to say a few words about the low-dimensional PDEs. Okay, how the neural network can be used to solve low-dimensional PDEs. So here the case that I will use is something called parametric PDEs. So the parametric PDE is essentially a low-dimensional PDE, but you parameterized by a certain parameter field, which I denoted by M here. Now, the example I'm going to give you is the simplest example, is the elliptic equation. So Lm is equal to minus divergence and M gradient. Okay, so this is the elliptic equation with a parameter field Mx. Now, when you give such a PDE, and usually you care about some quantity of interest, which I denoted by D here. And in this example, I choose D to be the so-called, for example, the Dirichlet-Neumann map. So what is the Dirichlet-Neumann map? So suppose I have the domain omega here, and I have the PDE, which is Lm equal to minus the gradient, divergence M gradient. Well, the Dirichlet map is defined as follows. So suppose you provided some Dirichlet boundary condition G on the boundary of the domain. So G is put on the boundary of the domain. And then you can solve for this PDE, and then you can study what is and you can, from the G, you can solve for the solution U. And then you can measure what is the normal derivative du dn across the boundary of the domain. Okay, so this map, starting from G all the way to du dn, is a map from the Dirichlet data to the Neumann data. And this is called the Dirichlet-Neumann map. And this is closely related to the Green's function of this elliptic operator. Now, why do I bring this example up? The reason is because such examples like the Dirichlet-Neumann map play a huge role in inverse problems. So here's a fundamental question of the parametric PDE, is that we can study something called a forward map and also called inverse map. So the forward map is a map that take your media M and try to derive what is my Dirichlet-Neumann map. But more importantly is the inverse problems. So this play a big role in for example, in applications like electric impedance tomography. So given the Dirichlet-Neumann map, which is something I can measure on the boundary by putting some electric current or electric potentials on the boundary, can I discover the media, the parameter field of my PDE? Okay, so that's the role of the inverse problem. Now, how's the neural network come into play here? Well, if you take a look at the forward problem and inverse problems, now they're defined through this PDE, and both of them is a high-dimensional function, linear high-dimensional function. Take a field and output another field, right? So therefore, this is a high-dimensional linear function defined through this low-dimensional PDE. And what neural network can do here is coming to represent this inverse and also the forward map. Okay. Now, let me just briefly talk about how the neural network architecture is designed for these problems. So one way to do that is to use some sort of, I will call, analytic formulas. So this is something what I personally have spent some time on, and this is what I will talk about in the next lecture, is that the simple example is that by using something called a back projection formula, you can get a rough idea about, you can get a rough approximation of the forward problem, for the inverse problem. And then by using neural network, what this allows you to tune certain parameters appeared in this back projection formula. And by doing that, you can adjust your analytic and the back projection motivated neural network to fit the data well, fit the training data well. So another line of work along in solving inverse problem is what I will call enrolling the iteration of optimization algorithms. Here, the main motivation is that in many cases, when you're trying to solve inverse problems, you write down objective function, right, like loss function, and then you run a certain kind of optimization algorithm to optimize this loss function. But now, suppose you fix a number of iterations, and then you unroll this algorithm, then you can think about this 10-step algorithm as applying a neural network with roughly 10 layers. And then what you can do is to try to optimize the parameters of this 10-layer neural network. Okay, Carola has done, and her group has done a lot of work in this direction, and including many people in the audience, and has developed very nice work in this along this approach. Now, no matter which approach you take, either the analytic approach or the enrolling approach, then eventually it becomes a supervised learning problems. So given the data, which in the case of inverse exam problem, so given the pair of tertiary normal map and also the internal parameter, what you can do is you can treat it as a supervised learning problem to fit for the neural network parameter, either come from the analytic formulation or come from this enrolling approach. Okay. So I will say a few more words about my personal work in this direction in the second talk. And if you're interested. All right. So the third part of the section 1 of my talk is I'm going to briefly talk about something called high dimensional to low dimensional reduction. So this appears a lot in the literature of applied math and scientific computing. So let me just briefly give you 3 examples here. One example is reduction from many-body quantum mechanics to the molecular dynamics. Okay. And at the next level, you can also have the reduction from the molecular dynamics to Boltzmann equation description, right, of the fluid. And then from the Boltzmann equation, you can also further reduce to the classical fluid description using Euler and the Navier-Stokes equation. I would like to, I will use this last example, this Boltzmann equation reduction. So here, the Boltzmann equation, the description is given by Fx dt. So this is a description of your particle densities at the location x and the momentum direction v and also time t. Now in the fluid equation, this is reduced to 3 variables: rho xt, which is your density, uxt, which is your speed of the fluid, and also ext, for example, which is the local energy. Or you can sometimes use the temperature as well. Now, one important problem in model reduction has always been the so-called closure problems. So here, in this example, for most of the fluid that we see in daily life, and this reduction works well. And in the sense that you can use 3 variables, rho and u and e, to describe a function f in the v space. So you see that in this reduction, the v variable is gone. In some sense, I delete the v variable. I make some assumption that the locally is Maxwellian, it's close to Maxwellian, but instead I described it with like 5 variables, rho, u, and e. So I reduce a function to 5 numbers. So this is done in classical literature, but the interesting question is that suppose you do not know that these are the 5 variables that you need to describe this high dimensional description, which is FV here. How can you find these 5 variables? Or how can you even decide how many variables you need? So this is the famous closure problems. So again, so I'm repeating myself. So in the closure problem, the first task is to find a small number of moments. So here I have 5 moments. And once you find these 5 moments, what we need to do is we need to find the dynamic equation for these moments. Because the whole goal of the model reduction is that once you reduce the model, you want to do simulation in these reduced variables, these reduced moments, rather than doing expensive calculations of the more complicated high-dimensional variables, high-dimensional descriptions. Now, the neural network has proven to be quite effective, at least in several cases for several applications. Now, to find the moments, the typical way is at least one popular approach is using something called an autoencoder. So the observation here is that if you want to say, I want to find 5 variables to describe my function in V, then at least one criteria it has to satisfy is that it should be possible for me to reconstruct my f from these 5 variables in a very well-defined way. Now, I might not be able to reconstruct perfectly, but I should get fairly close. So this first step here is called encoder. And the second step is called a decoder. So what you want to make sure is that if you encode first and then decode, you should get the original object back. Okay. Now, once you learn these moments, then what you need to do next is to find the dynamic relationship from these 5 moments in the previous step and to the 5 moments in the next step. Okay. So essentially what you want to do is that you want to make the diagram commute. So you have the solution ft at the previous step, and you get ft plus delta t. This is high dimensional representation. And you want to have the low dimensional representation involves rho t, ut, and et, and rho t plus 1, ut plus 1, and et plus 1. Essentially what you want to do is that you want to make sure that if I do this expensive simulation and then do model reduction, it should be the same as doing model reduction first and then doing this simulation in this reduced variable. Now, the question mark is what we need to figure out, because we always want to do cheap simulation at the lower level. So typically this is done by essentially one way to do that, to figure out what the question mark is to make sure to set up optimization problem and to make sure that this diagram commute. If you go this way or go that way, it will give you the same result. Now, there's a lot of other interesting questions coming in here, because typically, the reason why you want to find a low dimensional model is because the high dimensional model is too expensive. So you don't often come up with a lot of data in the high dimensional level. So therefore you need to aggressively doing simulations so that to gather more and more data. And now interesting question is that where do you gonna do the new simulation? And this is very much related to the exploration of AI. Okay. All right. Now I'm gonna move on to the second part of this talk, is how the PDE is gonna help neural network. So I'm gonna talk about 4 directions. One is that how PDE is gonna help design neural network architecture. And the second part is about the neural network training. This is related to SGD and GD, stochastic gradient descent and gradient descent. And then I'll say a few words about the generative modeling and also adversarial, generative adversarial training. This is GAN training. Okay. So let's move on to the first topic. So here is what I think about the neural network. PDE can help neural network in terms of architecture. So now the motivation is that if you take a look at most of the popular neural network architectures, there's always some very well-defined mathematical structure behind it. So for example, if you take a look at CNN, the mathematical structure behind it is translation invariant operators. If you take a look at ResNet, the mathematical structure is, I claim it's an ODE and a semi-group. And the ResNet is essentially can be viewed from a numerical discretization in time of these objects. And from also, if you take a look at something called attention mechanism, which has played a big role in recent neural network developments. So there's also a tensor product structure behind it. What you can think about is you have an input variable X as a 2-dimensional array by multiplying U and V2 matrices on the 2 sides of it, and then do some sort of nonlinear thresholding, and that will create the result. In some sense, it's doing fully connected in 2 different dimensions. It's tensor factorization of a more high-dimensional operator. Now we can also ask ourselves, is that how can PDE help us? Well, one way the PDE can help us is the following: is that when we study certain neural network applications, like for example the inverse problem I talked about earlier. And it makes much more sense if we can design a neural network to represent certain differential operators, certain operators which appear in these applications. 2 examples are pseudo-differential operator and also the Fourier integral operator. So pseudo-differential operator is operator which, like differential operators, but it also includes things like the convolutions and things like the fractional Laplacian and things so on and so forth. Now, these operators appear, for example, like the normal operator in inverse problems. So Fourier integral operator is another kind of operator. It's an extension of the Fourier transform, and it's very much related to the wave propagation. So whenever you have some kind of PDE, you have an inverse problem where you use wave as a mechanism for discovery. So often you will encounter the Fourier integral operator. Essentially, this is like the you can think about this what we call parametrics, or this is like an approximate exponential of the wave operator. Now, by studying these operators and try to study the sparse representation of these operators, we come up with certain new neural network architectures, which is compatible and which is also very effective in solving inverse problems. Here I'm giving you two pictures, two examples. The first example is something what we developed, what we call the BCR net, which I will say a few more words in the next lecture. Is fully based on the wavelet decomposition. So it's a generalization of the wavelet, sparse wavelet representation of the integral operators. On the right-hand side, we have something called a switch net. This is based on the sparse representation of the Fourier integral operator. We call it a switch net. And both of these has appeared to be, has been successfully applied to solve inverse problems. And I will say a few words about that in the next lecture. And now the second part of this, the second topic of the second part of the talk is on PD, how PD is going to help us do neural network training. So here I briefly touch about the two things. One is the mean field approach, and the other is the SGD training. Now, here I'm going to talk about the mean field description of the two-layer neural network, which has been quite well known in the literature in the past 3 or 4 years. So here X is my input. Y is my what I call response variables. Okay, so this is my response. So in the case of the two-layer neural network, what you want to do is that you want to find a two-layer neural network such that you take X and produce Y. Now, what is a two-layer neural network? Well, let me just draw a picture of the two-layer neural network. So you have the input X, which is maybe d-dimensional. In the case of a two-layer neural network, you're going to send X to take the inner product with a bunch of different parameters theta m. So X belongs to RD, and the theta I is also belong to RD. So what you're going to do is you're going to take the inner product. Once you're taking the inner product, you're going to put through this activation function, this nonlinear activation function, and then you average it, and this will produce a result, which we call denoted by fx. And I call this fx my model function. Now, in the case of the two-layer network, if you want to fit this response Y, then essentially, at least at the continuous level, what you want to do is that you want to optimize of all the possible neural network weights theta I, the following objective function. So here, what I'm doing here is I'm taking the difference of my model function with my target function, and then integrate it with certain risk measure, which is describing my data. Now, the idea of the mean field approach is to provide a PD description of this training process. Okay. Now here, I assume that I trained the theta I with a gradient descent. So in the PD description of the training process, what you do is that you lift all the theta i's. Instead of as a point in RD d-dimensional space, what you do is that you lift them to a measure on d-dimensional space. So you define the p theta, which is the empirical measure of these theta i's. That become a probability density on RD space. Now, once you do that, the model function takes the following form. Okay, it's easy to see that you directly get this formula by replacing the sum with a p. And then my loss function, written in terms of the new model function, takes this form. Now, the mean field description said that if you want to train a bunch of neural networks with theta i's with gradient descent, and then this lifted probability measure is going to undergo this PD description. So in this PD description, first you have this efficient derivative of your loss function with respect to the probability measure. And then once you have that, you're going to multiply with this famous operator, which is corresponding to the metric of the Wasserstein operator. And this will give you the time derivative. So therefore, this is sometimes also called a Wasserstein gradient descent. Okay. Now, this line of work, as I said, has been started about 3 or 4 years ago by these 4 papers. At least these 4 papers. I might miss some papers, but at least these 4 papers started this line of work. Now, they provide a very nice, satisfying description of this gradient descent dynamics in the PD language. So, however, I want to mention that this PDE itself is not easy to analyze because my loss function L here is not does not satisfy the so-called displacement convex property. So therefore, it's very hard, and even even the convergence of this is not. I believe is not fully settled, and it's even harder to get any convergence rate because we lack of this displacement convexity. Okay. Now, besides settle this convergence property of this basic PDE for two linear network, I think other interesting things include extending these to high-dimensional neural networks, so multi-level neural networks, and also other interesting architectures like CNN and ResNet. Okay, so there's also a slightly different view of in terms of the training. So previously I talked about two-layer neural network, mean field description with gradient descent training. We can also do stochastic gradient descent training for this loss function. And here, when you use stochastic gradient descent, every step you're not following strictly the gradient descent. You add a little bit noise. So one way to model this equation is to assume that the noise is actually Gaussian. So you assume this is Gaussian, or maybe even isotropic Gaussian. And then if, for example, I put a question mark here because this is debatable, but assume that it is Gaussian, then this SDE has a very, very nice Fokker-Planck description. So the probability distribution of my parameter is going to satisfy this Fokker-Planck equation. Now, I mentioned that whether this noise is Gaussian is a question mark or not. I would like to point out that in a very recent work by Voshtovich, and who's currently at the Texas A&M University, and he proposed a different PDE, which I believe is more reliable, more realistic in terms of handling the noise, and that will also give you a very interesting result. But I don't know too much about that work, so I will not say more. Now I will stick to this PDE. Why this PDE useful? And the reason is that this PDE is actually the so-called Wasserstein gradient descent of a different energy function, which is called free energy. It includes two parts. One is the loss function integrated with P, my probability distribution, and then plus the entropy of my probability distribution. So once you observe this, and well, has been around for a long time, and this is very well known. And once you take this viewpoint, then the dynamics of my theta, which now have a stochastic description because of the noise, can be written as the solution of this PDE. Again, this is the for sure derivative of my free energy and the Wasserstein flow. Now, the advantage of that is that we know once we have that, we can write down exactly what the equilibrium distribution are. So the P star is going to take a simple Gibbs distribution. Okay. Now, this view is useful because it helps us now to explain, because we have this extra entropy term. This will give certain cases give us convergence rate. And also, this also explains why the stochastic gradient descent like to go to the flat minimum rather than go to sharp minimum. Because flat minimum is a place where you have more entropy, so therefore it's more likely to find your parameter in a flat basin rather than a very sharp well. And finally, it also helps to explain why neural network trained with the stochastic gradient descent has better generalization error. Now, I'd like to also mention another application of this this viewpoint. This brings naturally to something which we call ensemble methods. So in this Fokker-Planck equation, if you take a look at here, so the metric that we used here is this grad P grad. This is called Wasserstein metric. Now, but in fact, Wasserstein metric is not only one you can use, right? You can also use something which is here, which I wrote something which is slightly more complicated. As long as this middle piece itself is a symmetric operator. Okay. So by introducing SVD convolution operator K, it's essentially a convolution operator. Here we, instead of using the P in the middle between these two, sandwiched between these two grad operators, you can also use something called a PKP. This is a diagonal multiplication with P and do a convolution with K and multiply P back. So this is also a symmetric operator. This is another kind of like gradient flow. This is gradient flow with a different metric. So in another paper by Liu et al., what they noticed is that this in fact is a description associated with the so-called Stein variational gradient descendants proposing the statistical literature. Now, the beautiful thing about this approach is that you can actually have a particle realization for this PD without adding noise and without adding doing density estimation. So if you try to represent this row density now with a few particles, theta 1 to theta n, both belongs to whatever r n dimensional space. If you have n is the dimension of your number of weights in the neural network, and these theta i's, if you run this dynamics, and this will follow the empirical distribution of the theta will follow this PD. Okay. So I think there's a lot of work that can be done in this direction, especially trying to understand the convergence property of the SVGD. And overall, I think that it's an exciting field and try to use PD as a starting point to design an ensemble-based method. Well, the next topic I'm going to talk about is this PD for generative modeling. Okay, generative modeling is also another big topic in deep learning. So here the idea is the following, is that I want to approximate a highly complicated probability distribution, which I denoted by Qx here. So X is my variable. Now, but I don't know how to sample from this distribution. Sometimes I don't even know what this distribution is. So the idea of the generative modeling is to say that I'm going to start from some simple probability distribution like a Gaussian. And then what I want to do is I want to define a map phi, which essentially is a diffeomorphism or some kind of coordinate transformation, such that the push forward of this phi, so phi push forward of your Gaussian, is going to be close to Q. Okay, so this is what generative modeling is doing. Now, what neural network comes, obviously you can use any phi function you want, but if, for example, X is in high-dimensional space, it's not easy to choose an appropriate phi. So what neural network comes in is to say that I'm going to parameterize my phi with certain parameters, and hopefully that's going to push my Gaussian distribution to a target distribution, which is close to Q. Now, how do we decide how to choose theta? One way to is to say that I want my target distribution P theta after I do the push forward is going to be close to Q. You can either measure in the KR divergence, or usually you can measure in this so-called reverse KR divergence. And sometimes one, for example, is appropriate for variational inference, the other is appropriate for MLE estimation. Now, how does a PD comes in? So here, I just want to mention one PD approach was developed by Wen and Yi's group back a few years ago. Is based on this very nice observation, is that so representing high-dimensional function phi's from X belongs to RD to RD is complicated. So one way to do that is to say that instead of representing this vector valued function, what I can do is to try to reduce this to a scalar valued function, lowercase phi. But how do I reduce this to a scalar valued function? Well, what you can think about that this coordinate transformation capital phi is not done in one shot, but it's done gradually through a certain flow. So the idea here to say is that I want, instead of describing this map in one shot, I'm trying to write down an ODE which achieve this map gradually. So starting from my initial location Z, which is sampled from Gaussian, I'm going to let it flow along this gradient field of this lowercase phi function. And then the good thing is that by using a simple calculation, using the fluid dynamic calculation, using the Lagrangian framework, one can show that the log of the density evolve according to the minus Laplacian of your this is what I call potential function. So essentially, these two equations gives you a continuous in time dynamics, tells you where the particle is going to go and how the density is going to change. Now, instead of parameterize this capital phi function with your parameter theta, what you can do is that you can parameterize this lowercase phi function, which is much easier to describe with the parameter theta, and then use ODE discretization like a forward Euler method, for example, Runge-Kutta methods, to discretize this ODE. Once you do that, it will naturally give you a ResNet, residual neural network. It's called residual neural network in terms of this, to implementing this flow. Okay, now then you see that it involves a few derivatives here. For example, here you have the gradient, you have the Laplacian. If you want to optimize the theta, you need to take one more derivative. But by using automatic differentiation packages like TensorFlow and also PyTorch, all these derivative calculation can be taken care of automatically. All right, so this is about the generative modeling. So we're trying to find a parameter theta such that the push forward of my probability density can match a target density Q. Sometimes it's very useful, but sometimes it doesn't give very good result. Part of the reason is that this KL measure of the probability distribution, the distance between two distributions, might not be appropriate for our applications. So one way to do that is to replace this inner KL divergence with certain maximization, which I'm written down here. Okay, so instead of trying to measure the distance between two probability distributions just by a simple formula like a KL, there will be relative entropy. What we can do is that we can try to replace this with a certain maximization procedure. Okay, so in the literature, theta is called a generative network, W is called a discriminated network, and this whole thing is called GAN. All right. Now, transfer to GAN looks appealing, but mathematically it also imposes challenges. The reason is because now, starting from minimization problem, you have a minimax problems. And these are in the literature is called a two-player zero-sum game with pure strategies, where pure strategies refers to have only one parameter theta and one parameter W. Now, it is well known that these problems are very hard to analyze, and in fact, it's I believe it's not even clear that the Nash equilibrium exists in this case because of a nonlinear parameterization. So one way we can do, which has become popular in the literature in the past 2 years or 3 years, is to consider the mixed strategy. So again, I'm going to lift theta and lift things to the probability distributions. So previously in two-linear neural network, I lifted the empirical distribution of the internal neurons to empirical distribution. So here what we're going to do is that we're going to introduce the distribution over all the possible over the parameters of generator and also the parameter of the discriminator. So once you lift this to probability distributions, you can write down this loss function in terms of the probabilities into this bilinear form. Okay. And sometimes we also include entropies on the P densities over the generators and also minus the entropy of the densities of the discriminators. Now this problem is nice because in terms of probability space, and this is convex concave problems. So this is a linear in P, linear in Q, so it's good. This is convex in P, this is concave in Q. So therefore you have a convex concave problem. And this mixed strategy problem is guaranteed to have a unique solution. Now, one thing first come to mind is how do you solve a problem like that is to use gradient descent, for example. Why do we want to use gradient descent? Well, the reason is but the gradient descent, okay, so these are high dimensional probabilities. So in practice, if you want to optimize it, you want to do calculations on it, you're more or less forced to use particle methods. And once you use the particle methods, this corresponds to the gradient descent and gradient ascent of your probability densities in this Wasserstein metric. So here I write down these equations. This PD is very interesting because the system, and this is something called a Markin-Vlasov type because you have a diffusion, but at the same time you also have a nonlinear term, which couple the nonlinear term of the other variable at the density. Now, one key question, which I personally is very interested in, is to see, does this system converge for large beta? So for large beta, you have a small diffusion. Now, when the diffusion is large, and this set of equations is guaranteed to converge to the unique minimum. But when you have a very small diffusion, it's not clear whether it converges. I mean, so I believe it's a very hard PDE problem. If anyone's interested in it, I think this is one interesting problem to work on. Now, because we cannot prove that this system converges, so there has been some recent work and try to get around this problem. One work I would like to mention is this work come out of, I think, NYU's group, is that try to use, instead of using this diffusion, but you use a burst test process. And I think they can prove some convergence result, but again, I think there's a lot left to be done. So in the remaining one last minute, what I want to mention is that with Chao Ma, a colleague at the Stanford University, we have also been trying to find ways to address these problems. So instead of using this burst test process, what we decided to do is using something called quasi-static dynamics. So the goal is to split the minimax problem into an outer minimization and inner maximization. And the idea is that let's do some quasi-static dynamics in the sense that let's fix the P and try to work out the maximization problem. It turned out that, I mean, one can actually solve the inner problem explicitly. And in terms of computation, this would be done by using a quasi-static kind of like a particle method. And once you solve the inner problem, you can use it to, sorry. Yeah, once you solve, you can plug into the outer equation, outer minimization, and try to find the dynamics to optimize P. Okay, so in a recent paper, we showed that this process is well defined, but there's also a lot of things needs to be done in terms, for example, the convergence rate and other things. So, so this is the end of my talk, and all my research is supported by NSF, and I think I give you a very, very quick overview about these topics, and some of things I only, for almost everything, I only just scratched the surface, but I hope this will be useful to at least provide my personal perspective on how the neural network connected with PDEs. Thank you. Hello?
Excellent. Thank you so much, Lexing. I think that was a really great overview. Can you hear me?
Yeah, I can hear you now. Yes,
okay.
Thanks.
Excellent. Super. It was really wonderful. Thank you. Other questions from the audience or from the online or remote audience? Please just speak up. Probably that's easiest. Maybe I can start with something like saying, if you go back to your Wasserstein gradient flows, you had, well, the one where you added the diffusion, maybe the where you started with the 2-layer. So before the, yeah, exactly here. So yeah. So basically, is it that your new energy is now displacement convex because of the diffusion or not?
Oh, in this case, yes. In this case, it is displacement convex. Yes. In this case, the reason, right. So the reason why that this is nice because it displays convex, so you can have a convergence rate. Yes.
Exactly. So is it possible at all, do you think, to recover the convergence rate, for instance, of the original problem without the diffusion by taking a limit here or something like that? By taking going to infinity, I guess.
I think, yeah, let me clarify one thing. I think that you bring a good point. So in fact, the two systems are actually quite, my kids was playing this, so let me just choose a black color. So for example, in the 2-layer neural network, so this probability, so suppose my X's belongs to RD, so therefore my neurons in RD. So the probability distribution is actually is on RD.
Yes.
The probability distribution is on RD. But now if you count how many internal parameters I have theta 1 all the way to theta m. So therefore, if you concatenate the theta 1 to theta m, the whole theta vector is actually belongs to RD times m. Okay. Yes. So in this slide, when I talk about mean field description of 2-layer neural network, my probability density is on the d-dimensional space. But now in the second slide, I minimize over all possible theta, right? So when I minimize over all possible theta, this theta, as I said, belongs to RMD now. So it's this. So on this slide, we're actually doing a probability. So P is actually RMD.
Right. Okay.
So this is a diffusion. So this is a Fokker-Planck equation on a much bigger space. So in fact, the previous description is, you can say, even though it's already a probability distribution, but more compacted than this one. Okay, so that's why the previous distribution, there's no noise because I'm doing gradient descent training. So this loss, and also one difference is that if you take a look at the previous description, the loss is actually quadratic in P, right? Because I have something linear in P and then squared. So this is a quadratic in P.
Yeah.
But in the second slide, when my probability distributions belong to RMD dimension, this loss function is actually is multiplied with P. So therefore it's linear in P. This main piece is linear in P. And I added this entropy to make it less strictly convex. So in fact, these two equations, the one on the previous slide and this slide, they actually live in different spaces. Yeah. So the short answer to your question is that maybe there's a way we can actually take the limit, but it's not obvious to me. And I think it probably, I mean, I think it's probably, yeah, they're talking about different things, I think.
Okay, great. Thank you, Lexing.
Sure.
Are there other questions? Other questions online? Yeah, I think people need to warm up, Lexing.
Yeah, it's okay, no problem.
Thank you so much. It was really, I found it very, very interesting. Thank you so much. And I look forward to tomorrow.
Okay, yeah, great. I'll see you tomorrow.
Thank you so much. Bye.